The next subject we're going to talk about is something called quantum numbers, and I think you have a very small sense of what a quantum number is, you just don't know it yet right now. So first, before we talk about quantum numbers, let's talk about electronic configuration of elements, and it's been a while since we did this, but remember this was the electron configuration stuff was the 1s1, 1s2 kind of stuff. So if we wanted to write hydrogen's electronic configuration, it's in the first row, and we would say that was 1, and it was in this subshell, right? So 1s, and it has 1 electron in the s subshell, so 1s1. If we wanted to talk about helium, we would say that it's in the first row again, and that's a 1. And its electrons are in the s subshell, because remember I told you to put helium here a lot of the times. And it's got 2 electrons in the s subshell, so 1s2. Talking about neon, if we wanted to write neon's electronic configuration, we would say it's in the second row, but it still has the electrons from the first row, right? So it's got the 1s in both of those electrons, right? It's got 1s1, 1s2. It's got 2s1 and 2s2 electrons as well, 2s2, and it's got all 6 of the p subshell electrons, right? So 2p6. Okay, so this is electronic configuration. If we wanted to do it for fluorine, right, for this one, let me put this one over here. Sorry, let me move that. To do this for fluorine, it would be very similar to neon, only it doesn't have that 6th p electron. It's only got 5. So 1s2, 2s2, 2p5. Okay, what does this have to do with something called quantum numbers? Well, quantum numbers allows you to talk about which electron we are kind of looking at in question. So the 1, 2, this 1 and 2 thing. Okay, if we want to talk about an individual electron, we use something called quantum numbers. And you need to know about quantum numbers, but you're never going to be asked to assign quantum numbers on the exam. That's beyond the scope. But it does, quantum numbers, the concept, will be on the exam as far as I'm aware. So quantum numbers. Let me write what they are. Wow, that was interesting. The page kind of just shifted on me. Quantum numbers. So quantum numbers. And what are they used for? They tell, I'm going to put this in parentheses, they tell the address of an electron, essentially. Okay, let me zoom in just a little bit here so I have more space to work with. So they tell the address of an electron. Okay, there are 4 quantum numbers. 4 quantum numbers, QN. The 4 quantum numbers are N, L, M sub L, and M sub S. Okay? N is called the principal quantum number. Principal. Like P-A-L or P-L-E. Let me look before I get it spelled incorrectly. P-A-L. Principal. Like the, I guess like the school kind, I think. Okay, principal quantum number. L is called the orbital angular momentum quantum number. M sub L is called the magnetic quantum number. Number. Okay, and M sub S is called the spin quantum number. I don't know why I wrote quantum number down for magnetic, but I didn't for the other one. So it's just, imagine the word quantum number is after all these. Principal quantum number, orbital angular momentum quantum number, magnetic quantum number, spin quantum number. Okay, and these have something to do with the kind of address of an electron. So let's talk about helium real quick. If I wanted to visualize these electrons, we did this very briefly last year in some notes. But if we want to write the 1, I'm going to start here with the first, the 1s electrons, right? And there's only 2 electrons. The 1s electron has 1 orbital, and the electrons, 1 spins up, 1 spins down. I almost need a keyboard shortcut for erase. I'm gonna do you guys a favor and figure out the keyboard shortcut for erase so I can do that. Okay, if we want to talk about the 2s, it's at a higher energy level, right? One spins up, one spins down. 2p is at a slightly higher energy level than 2s, but not up to like where 3s is. And there's 3 orbitals in that. 1, 2, 3. One's up, one's up, one's up, one's down, one's down, one's down. Okay, you might be thinking, well, what does this have to do with quantum numbers? Okay, the different energy level you're at, that's n. So the first one here and the second one, this is n equals 1. This is n equals 2, hence the 1 and the 2. Okay, L is the angular momentum orbital quantum number. And L talks about if you are in the s orbital or if the electron is a part of, say, the p orbital. Okay? And L can be, as far as a number goes, let me write L over here. So first of all, N can be anything from 1 to infinity. Okay? L can be 0 up to n minus 1. Okay? Let me put that in parentheses so we don't get... So L can be 0 to n minus 1. Okay, here is where L is 0. L is... Let me write this one more time. So S is where L is equal to 0. So S is 0 for our quantum number L. And P is where L is equal to 1. Okay? So for quantum numbers, for L, 0, 1, 2, 3 correspond to S, P, D, or F. Okay? And you could have a fourth one and it be G, but this would be a hypothetical electron. Because, remember, as far as the periodic table goes, this one down here is when the F orbital is completely filled, so there's no real G, or there's no real G subshell, I should say. All of the F orbitals are filled, so the F subshell is filled at this element. We haven't ever made one past that. Okay. M, the magnetic one, ranges from minus L to L. And what that means, if we look here, so here S is 0. So if we look at these electrons right here, then M is 0 for this, right? If it ranges from negative L to L, if L is 0, then M is 0. Here, L is 0. Here, L is 1, right? So L is 1 right here. Here, L equals 0. So M sub L would equal 0. Okay, if L equals 1, right, if we're talking about the P subshell, M ranges from negative 1 to 1. And what that means is I can have this one, I can call this blank negative 1, this one 0, and this one 1. Okay, so these quantum numbers tell you kind of where, it's like the address for the electron, right? And last but not least is the spin quantum number, and it simply is the electron spin up or spin down, right? So if I want to identify an individual electron, I'm going to go ahead and do that, even though it's not going to be asked of you on the exam, because I think it will give you a better understanding of these quantum numbers. But MS is simply, is it spin up or spin down? And we assign the spin up, spin down as either. Like if it's spin up, we call that plus 1/2. Why it's 1/2 is because of a solution to the Schrodinger equation. Just let it go. That's what it is. It's plus 1/2. Okay? This is minus 1/2. All right, let's say I wanted to look at a particular electron and tell someone that I was looking at a particular electron. So let's look at the element phosphorus. Okay, so phosphorus has a 1s2, 2s2, 2p3 electron configuration. Oh, sorry. 2p6, I was one row above in my head here. 2p6, 3s2, 3p3. Okay. Let's say we wanted to talk about a particular electron. And I think the diagrams do the best job at talking about an electron, but let's look at the 1s electrons. Okay, so the 1s electron, we've got both of those. Okay, we've got both of the 2s electrons. Sorry, and then when you draw these guys, it's not a double arrow, it's like a half arrow. So up like this, down like this. Okay, the 1s I'm going to put off to the side. I'll put the 2s next to it. So 1s, 2s. Okay, it's got all 6 of the 2p6 electrons. And I've filled those incorrectly. Those fill one at a time. I'm going to redo that just so I don't instill a bad habit in you. So these fill one at a time like this. I apologize. Okay. It's got both of the 3s electrons. And it's got it's got 3 of the 3p electrons. Okay, let's say you wanted to tell someone that you were talking about this electron in particular. Okay, that one. The way you would do that with quantum numbers is we would say n equals 3, right? It's in the third. This is 3s2. Sorry. This is our 3s, and this is the 3p. So n equals 3 for that electron, right? It's in the third shell. Okay. L is equal to 0. Right? S, let's see, where did I write that down? Over here. Yeah, so S is equal to 0 for L, right? So L is equal to 0. M sub S is equal to 0, right? If L is equal to 0, M sub S is going to be equal to 0. And sorry, I just wrote this one wrong. It's not M sub S, it's M sub L. M sub L is equal to 0. M sub S is equal to minus 1/2 because it's spin down. Okay, let's try to do another one, Mr. Woodard, without making any mistakes this time. So let's pick this one. This one right here. So how would you tell the reader you were talking about that electron in particular? And using quantum numbers, n is equal to 3 again. L, this time, we're talking about the p subshell, so L is equal to 1. Okay, M sub L is equal to minus 1, right? Minus 1, 0, and 1. That's the M sub L. That's how you label that. Then M sub S is equal to plus 1/2 because it's spin up. So there is no other electron that has the same address as this electron. Okay, so all the quantum numbers, you can never have the same quantum numbers. Okay, you can have, if I want to talk about, let's say we're looking at the very next element, so sulfur. This one. Okay, so let's say this is for phosphorus, right? If we want to turn this into sulfur, we add a proton and another electron comes on. Let's say we want to talk about that electron right there. Okay, the only difference here is if we're talking about this electron this time, n is still equal to 3, L is equal to 1, M sub L is equal to minus 1. But now that electron, M sub S, is equal to minus 1/2. Okay? You won't be asked to assign these on the AP exam, but you do need to know that no electrons can have the same 4 quantum numbers. So these have 3 of the same, but not the 4th one. That is called the Pauli, see if I spell it right, Pauli exclusion principle. Okay? You can't have electrons occupying the exact same orbital with the same spin, essentially. So that's quantum numbers. I hope it didn't get too confusing, but that's where the kind of electronic configurations come from.